1290. Originally built of wood, the Long Bridge had a chapel at either end. Constant repair work was needed, and shortly after 1535, it was encased with stone. The new stone bridge was very narrow, and over the years was widened as the traffic increased. On January the 9th, 1968, two arches at the western end of the bridge began collapsing. Repair work was started immediately, but the partial collapse helped to highlight the need for a new bridge. And in 1972, studies commenced on planning an alternative Torridge Bridge and a bypass for Bideford. MRM partnership were appointed by the Department of Transport, and orders were placed for an extensive site investigation to commence. The preferred location for the new crossing was 1 mile downstream of the old bridge. A number of configurations for the 650-metre crossing were considered. These included both cable-stayed and suspension bridges. The final decision, after consultation with the Fine Arts Commission, was for an 8-span glued segmental bridge. Larry Brindle, the MRM resident engineer, tells us more about the project.
Bideford Bypass is an 8-kilometre road scheme which runs from Westley Junction on the eastern side of the River Torridge to Fairy Cross in the west. There are also 3 kilometres of side roads associated with the scheme, and there are 2 major roundabouts, one at Haywood Road and one at Abersham Cross. In addition to that, there's an interchange at Winsford. There are 6 culverts, 2 small bridges and 2 major structures. Two major structures are Kenwith Viaduct over the Kenwith Valley about halfway down the scheme, and Torridge Bridge, which crosses the River Torridge right at the eastern end near Westley.
The Torridge Bridge is 650 metres long in 8 spans. 3 types of foundation were needed: large reinforced concrete pads for the abutments and piers 1, 2 and 7, caissons in mid-river for piers 3 and 4, where the spans are 90 metres with 25-metre headroom to permit ship passage, whilst piers 5 and 6 are founded on large diameter board piles. After the design of the 2 important structures and the road, the necessary documents were prepared, tenders were sought, and the successful contractor, Edmund Nuttall, commenced work in October 1984. After an access road had been constructed, work commenced on a temporary access jetty, which thrust out into the river from the west bank to gain access to the river foundations to piers 2, 3 and 4.
A main feature of this bridge, apart from the fact that it's glued segmental precast, is the fact that we use caisson construction where foundations have to be very deep in the centre of the river.
A steel cutting shoe was constructed on the floor of the Appledore dry dock, and the base 3 metres of the 2 caissons were concreted alongside each other. The structures are cellular, each caisson having cross walls dividing it into 8 separate cells. When this work was completed, air decks were inserted in the 8 openings to create a floating structure. To improve the freeboard, steel panels were bolted to the side of the concrete, and compressed air was pumped beneath the air decks to increase the buoyancy. Then the tow up the river to the jetty could be commenced. After all the necessary calculations had been carefully checked, the first caisson was floated out on a spring tide early in 1985. With little room to spare between the walls of the old dry dock and only 150 millimetres clearance over the entrance sill, there was much relief when the operation was successfully accomplished. final ballasting and air tightness checks had been carried out, the tug set off to position the new caisson against the temporary jetty at the new bridge site. Precise positioning of the new foundation was made doubly difficult in that this operation was carried out at night to suit the most favourable tides. After positioning, the caisson was settled onto the riverbed and the air decks, which are no longer required, were removed. The float-out operations were repeated 2 weeks later for caisson 4. The concrete walls were then raised. Wet excavation of the sand and clay within the caisson was undertaken by grab. The caisson was settled 10 metres when a cobble layer was encountered. A permanent concrete air deck was installed, incorporating an airlock, and the caisson pressurised up to 30 pounds per square inch to evacuate the water within the caisson. Excavation then continued, with miners working on rotary shifts excavating the remaining 5 metres of material by hand. This operation continued until the caisson settled to the level of the bedrock. Here, the first stage of the operation is underway, with work continuing from the jetty, raising the walls of the caisson to their full 16-metre height before the sinking operations could commence. When the grabbing operation was completed, compressed air sinking commenced. Rigid safety procedures were necessary, and at the end of each shift, the miners went through a 2.5-hour decompression procedure in the on-site decant lock to ensure complete acclimatization to natural atmospheric pressure. Access to the caisson below was by way of a gowering airlock. When the bedrock had been reached, a 500 cubic metre plug of concrete was pumped into place. Work was then continued on the construction of the large reinforced concrete fender, which will protect the base of the column from possible ship impact. After the installation of caisson 3, caisson 4 was raised and excavated in the same way. Both these foundations were now ready for the column construction, which would eventually carry the superstructure. During these activities, the other foundations and the spill-through abutments were progressing, the foundations to piers 1 and 7, and the large diameter board pile foundations to piers 5 and 6. The foundation to pier 2 was being constructed within a steel sheet pile cofferdam adjacent to the west bank. During the summer of 1985, fencing defined the line of the new road. Earth and stone hedge banks were constructed to blend into the Devon countryside. Earth-moving operations continued to form the embankments using material excavated from the cuttings throughout the site. The deepest of these cuttings required a retaining wall, which was tied back using rock anchors. This eventually afforded access to the other major structure, which would span the Kenwith Valley. Soon an impressive birdcage of scaffolding was erected to support the in-situ deck of the new bridge. The bridge deck was stressed in 4 65-metre lengths, and as each length was stressed, it allowed the scaffolding to be removed and to be re-erected, ready for the next bay of construction. Eventually, the full 270-metre length of the bridge was completed, and a scaffold cleared away to expose the slender structure. The geometry of the road required the Kenwith Viaduct to be designed with a sag curve. The precast segments which would form the superstructure of the Torridge Bridge were precast on site. Early in 1985, the precast shed had been completed and the sophisticated concrete mould installed, and casting of the precast concrete segments commenced. The contractor elected to use the short bed method of casting. Reinforcement cages were prefabricated in steel-framed jigs. This ensured the careful positioning of the stressing ducts and the anchorage pods. After checking and tack welding, the cage was lifted and positioned on the bed of the mould. The previous unit was then precisely positioned to suit the required geometry of the bridge. Extreme care had to be taken to ensure that any slight movements that may have taken place during casting were corrected. The computer program not only corrected for these movements, but also deflections and shrinkage factors to ensure that when the segments were fitted together, the final profile of the bridge would be correct. The side panels are then positioned and the core shutter travelled into place. After final fixing and adjustment, concrete placing commenced. The pumped concrete is placed against the previously completed segment, thus ensuring that the two faces match perfectly and the deck cambered to suit the road profile. The following morning, after a geometry check, the concrete strength is tested to ensure that the newly cast element can be moved. The segment is then stripped, separated from its matched segment and travelled out of the shed on the wheeled bed. A fixed gantry lifts it and lowers it onto the transporter for conveying to the storage area. The specially designed transporter is capable of unloading and reloading the segments itself. This is accomplished by the use of jacks and outriggers, which swing out from the side of the unit and obviates the need for conventional craneage. Completed segments, weighing from 105 tons to 55 tons, were stored on the partially completed roadworks. This cycle of operations continued until the 251 segments which go to make up the bridge superstructure were completed. Back on site, the foundation work was well advanced, and the 25-metre columns were starting to rise from the foundations. The launching gantry had been delivered to site in sections and was being assembled on the road embankment adjacent to the west abutment. Further temporary works were being installed to support the out-of-balance segments, which would eventually be added to the first cantilever. After testing and commissioning, the gantry was ready to be launched forward, and the superstructure erection could commence. Once the launch girder is in place, segments are placed alternately, one each side, to maintain balance. After every 4 segments, 2 each side, permanent stressing is completed, and legs attached to the girder are moved out into a new position, thus allowing the girder to maintain the balanced stability of the cantilever. This procedure continues until the cantilever is completed. Here, segment Pier 1, 3 West, is being reversed up to the gantry and fixed ready for launch. The segment is travelled out. After lowering and turning, it is positioned with a small gap to permit the spreading of an epoxy glue to the face of the segments. The two-part glue served to lubricate the mating faces and to form a weather seal. After final positioning, temporary divvy-dag bars were stress-bolted through the top and bottom flanges. When 4 segments had been placed and temporarily stressed, permanent stressing cables were threaded through the ducts. 19 cables formed a tendon, which, when stressed, allowed the temporary stressing bars to be released and set aside for reuse. This cycle of operations continued until a complete cantilever of 33 segments, weighing 2,200 tons, was completed. After completion of the cantilever, a mid-span in-situ joint is constructed and the next launch forward is carried out. The nose of the launch girder is travelled out and connected to temporary stub columns attached to the pier. The next pier head segment is then placed on the bearings on top of the concrete pier. A further launch forward then takes place to position the gantry ready to build the next cantilever. The hanging cradle supports the in-situ mid-span concrete joint. To ensure that no differential movement takes place, 2 temporary steel hinge structures are bolted to the bridge to tie the 2 cantilevers firmly together. Reinforcement is placed, continuity stressing ducts positioned, and concrete poured to complete the joint. After curing, continuity tendons are stressed through this joint, firmly connecting the new cantilever to the previous spans. Preparations could now be made to launch the gantry forward to the next column. Tracks are laid and the travelling legs made fast to the bridge deck. When all is ready, the signal could be given and the 160-ton, 120-metre-long gantry slowly but surely move forward, so that once again its nose could be connected to the next pier. The bridge bearings were then positioned on top of the pier. The next 105-ton pierhead segment is delivered to the gantry. Slowly but surely, it is transported to the column head. Precise positioning is obviously vital to ensure that the next cantilever meets the previously completed section. In this way, 7 cantilevers marched across the river estuary, and the inhabitants of Bideford became aware of the imposing size of the new structure. The expansion joint at deck level and the in-situ edge beam were installed, and by the end of 1986, the Torridge Bridge was structurally completed. This was followed by installation of the curbing, service ducts, and deck waterproofing. Whilst all this activity was happening, the roadworks were well advanced. Lean concrete was placed, followed by the asphalt surfacing. This enabled the western end of the road to be open to traffic. And so, 2.5 years later, the time had come to celebrate the completion of the bypass with its two splendid structures. In a simple ceremony, the Bishop of Crediton blessed the new bridge. The opening ceremony was performed by the Lord Lieutenant of the county.
It gives me great pleasure to open this bridge, and I hope that it brings all the benefits which we have foreseen to both North Devon and the relevant parts of North Cornwall.
Preceded by police outriders, the cavalcade drives off to inspect the completed bypass. Not long afterwards, the traffic was passing freely along the new road and past the retaining wall, now faced with local stone. And so, Bideford now enjoys the benefits which a new bypass affords. And the Torridge Estuary boasts two fine bridges, built 500 years apart.